The next topic I'd like to talk about is called integration by parts. No pun intended, this is part one. As a warming up exercise, let's remember some stuff. When we defined the definite integral from a to b of f of x with respect to x, we divided the interval from a to b up into subregions of width delta xi. Within each subregion, we picked a number, x equals ci. We calculated the function at that point, multiplied by the delta xi's, added them all up, and then took the limit of the Riemann sums. In this sum, this is a number, and this is another number. They are being multiplied together. In the integral, this is the name of a function and the name of the independent variable. This really is just kind of a bookmark. It reminds me of what the variable of integration is. Also, the way it's written reminds me of function value times delta xi. But really, in this integral, this is not multiplication. Dx is not a number. And this is not f of x times a number dx. In dy dx, our notation that we usually use for derivatives, this is the limit of delta y over delta x as delta x tends to 0. It is the limit of fractions, which is why we write it this way, but it's not a fraction itself. It's not some number dy divided by some other number dx. These things are definitely not multiplications and fractions. Having said that, it's sometimes useful to pretend that they are for memory purposes. If y were a function of u and u were a function of x, one of the versions of the chain rule says that dy dx is dy du multiplied by du dx. This really is multiplication. I'm taking some function of u and multiplying it by some function of x. It looks like this is just multiplying fractions together and canceling the du out. That is not what's happening there. We write it like this to help us remember the chain rule. The notation is justified from where these things came from, delta y's over delta u's times delta u's over delta x's, but we have to let the delta x tend to 0. It's a convenient memory thing, a mnemonic, I think they call them. If you have an integral like this, integral of the 9th power of 2x squared plus 5 multiplied by the function 4x and then integrated with respect to x, this thing down at the end is not multiplication, really. This is not 2x squared plus 5 to the 9th power times 4 times x times dx. But it's often convenient for us to pretend that it is, and we base this on where these things came from again. If u was 2x squared plus 5, the derivative of u with respect to x is 4x. If I pretend that this is a fraction, which it isn't, I would write du is 4 times x times dx. My integral has a 9th power of 2x squared plus 5, a 9th power of u, so I could just write it this way. 4 times x times make-believe kind of dx is du. So this thing down at the end, I'm going to pretend it's just multiplication. If I do that, 4 times x times dx is du. This turns my integral into the integral of u to the 9th power with respect to u, which is an integral that we know how to do. Antiderivative is 1/10 u to the 10th power plus a constant of integration, and then put in the fact that u is 2x squared plus 5, and you've got your answer. If you wanted to do a check on this, you could take the derivative of that answer and make sure that in the end, you get the 9th power of 2x squared plus 5 back again. You'll use the chain rule to do that, which is no big surprise because doing this, turning it into this kind of integral, and then doing that integral is secretly using a disguised form of the chain rule. It's because the derivative of 2x squared plus 5 shows up as a factor. Based on these comments, we're going to do something that just seems crazy. If I have a derivative, say du dx, and I multiply it by this non-thing, this thing that's not a number, dx, we're going to start calling that du. We're pretending that it's fractions and that the dx's and the du's are actual numbers, which they're not. We'll do something similar if we have other functions. So dv would be the derivative of v with respect to x times dx. Why would a person do this? This is the product rule. Suppose that you had two functions, u and v, that depend on x. You multiply them together so you get a new function that depends on x. The derivative of that new function is figured using the product rule. You take one of the functions and multiply it by the derivative of the other one. Then you take the other function and multiply it by the derivative of the first one and add them up. So you should be familiar with this. This is just the product rule. If you have two things that are equal to each other, like, for instance, this quantity and this quantity, and you do the same thing to both of them, the results have to be the same. So I'm going to integrate both sides of this equation with respect to x. Now, on the one hand, derivatives and integrals are sort of inverses of each other. When I say integral of something with respect to x, I'm trying to find a function whose derivative is the something. So here, listen to the words here. Here, I want to find a function whose derivative is the derivative of u times v. Obviously, u times v would work. So I'll write down u times v. Technically, I should write down plus a constant of integration, but as we know, if I can find one antiderivative, I'll add a constant of integration at the end and I'll have all of them. So I'm not going to concern myself about that. U times v over on the left-hand side. Here, I've got the integral with respect to x of the sum of two things. Now, we know from Calc 1 the integral of a sum, you could do this. You could figure out the integral of the first chunk, the integral of the second chunk, and add them together. Things are getting a little bit more concrete now. This thing, du dx multiplied by dx, we said we were going to call that du. This thing, derivative of v with respect to x times dx, we said we were going to call that dv, so we're going to use our abbreviations now. If you do that, dv dx times dx is dv, du dx times dx is du. So weirdly, the following statement should be true. U times v ought to be the integral of u dv plus the integral of v du. If we didn't know what those v's and u's and dv's and du's were supposed to represent, this would look like it's complete gibberish. If you subtract this term from both sides, you find out that the integral of u dv is u times v minus the integral of v du. This is what's called the integration by parts formula. It's going to let us do certain integrals that we would otherwise be unable to do. So we're going to start off with some integration problem. We want to integrate f of x dx. And perhaps f consists of several factors. I can group stuff together to constitute the u. If I do that, then all the other factors, including the dx, have to be under the umbrella of the dv part. If we write out the integration by parts formula, if we picked the u and v correctly, it's possible that the integral that remains is easier to do than the integral that we started with. And then we take care of the easier one and we're done. That's the generic plan. So I want to find an antiderivative for x times cosine x, really with respect to x, but we're thinking of this as x times cosine x times dx. I've got three things sort of multiplied together. There are various ways that we could group these things. I'm going to try this. I'm going to try letting the u equal to that x. That means everything else to the right of the integral sign has to make up dv. So dv is going to be cosine x dx. If I take the derivative of u with respect to x using our calculus 1 techniques, I get 1. If I pretend these are fractions, which they're not, du would equal 1 times dx. That is to say, du and dx are going to be the same thing in this problem. When I do integration by parts, and it comes time to write down du then, I'll just write dx. dv is supposed to be cosine x dx. If these were fractions, which they're not, dv over dx would be cosine x. That means v has to be an antiderivative for cosine x, and one such antiderivative is sine x. As I said before, we'll wait till the very end to put the constant of integration in. So writing down u times v minus integral of v du, we write down x sine x minus the negative of cosine x. My antiderivative is going to be x times sine x plus cosine x plus a constant of integration. Now, since this technique is new to us, it's a good idea to make sure that this answer is right. So I'm going to take the derivative of my answer here, and if things are correct, I ought to get x times cosine x back. Derivative of x sine x plus cosine x plus a constant. The derivative of a constant term is 0, so I'm not even going to write that one down. The derivative of x times sine x, I have to use the product rule on this. It's the first function, x, times the derivative of sine x, which is cosine x, plus the derivative of x, which is 1, times sine x, plus the derivative of cosine x is negative sine x, and a miracle happens. The sine of x plus the negative of sine x cancels each other out. All that remains is x times cosine x. We see that our answer is right. One common strategy when you're trying to do this is you want to pick the u function so that its derivative is easier to handle in some sense than the original u was. Also, many people advise you to try to take the dv to be the most complicated thing that you'll be able to integrate in order to carry out your plan. This is with the idea of getting as much trouble out of the way as you can early on in the game. A very similar example. I'd like to find the antiderivatives of 3x plus 2 multiplied by e to the x. I'm going to try doing this with integration by parts. The 3x plus 2 is a linear polynomial. It's of the same general nature as x from the preceding example. So I think that making u equal 3x plus 2 ought to work out for me, unless what remains is too difficult for me to integrate. So I'm going to let u equal 3x plus 2. dv is the rest of it, e to the x dx. The derivative of u with respect to x is 3, which is a constant. Du is 3 times dx. In this example, du and dx are not the same thing. They are constant multiples of each other, but they're not the same. When I write out the integration by parts formula, when it comes time to write down du, I'm going to write down a factor of 3 and a factor of dx. dv we picked to be e to the x dx. dv dx would be e to the x, meaning that v has to be an antiderivative of e to the x. One antiderivative is e to the x. So when I write down u times v, that's going to be 3x plus 2 multiplied by e to the x. That's this chunk, minus the integral of v du. V is e to the x, so write that down. And as we said, the du will be written as times 3, kind of, sort of, times dx. If you integrate that, which is easy because the 3 is a constant factor, you find out that the answer to your original problem is 3x plus 2 multiplied by e to the x minus 3e to the x plus a constant. If you want, you can group these terms together and factor an e to the x out, and you'll be left with 3x plus 2 minus 3. You'll be left with 3x minus 1 times e to the x. And as I said earlier, if you can check your answer, it's always a good idea. Take the derivative of 3x minus 1 times e to the x and see if it's what it's supposed to be. The derivative of the constant term c is 0. Do the product rule, group terms together, and you find out that the derivative of the interesting part of my answer up here is 3x plus 2 times e to the x, and that's what it's supposed to be. This procedure, when you first see it, seems completely crazy, but as we've seen, it actually does work. You cannot solve all integrals using integration by parts, only some, and those that you can do with parts, you have decisions that you have to make. You have to pick what the u and the dv are going to be. And even if you can do the problem with integration by parts, if you make a bad choice, it's not going to go well. So I'm going to deliberately mess a problem up here. I want to find the antiderivatives of x times e to the x. I've got a factor of x. I've got a factor of e to the x. I've got kind of, sort of, a factor of dx. There's different ways I could group stuff together, but I'm going to deliberately make a bad choice here. I'm going to pick the u to be the e to the x. I'm going to pick the dv to be x times dx. The derivative of u with respect to x is e to the x. du is e to the x dx. Well, it didn't get any worse, at least. dv is x times dx. dv dx is x. That means that v has to be an antiderivative for x. V is 1/2 x squared. Writing down the integration by parts formula, we write down u times v minus the integral of v du. If we could get that, we would tack our constant of integration on and be done. Unfortunately, the 1/2 doesn't bother me any. You could factor the 1/2 out in front of that last integral. You're going to be left with trying to calculate the integral of x squared times e to the x. The original problem was x e to the x. This is not simpler than the original problem. Actually, it's more complicated because I've got the second power on that x instead of the first power. This approach is not going to work. And it's not integration by parts formula fault. If you let the u be x, everything will work out just fine for you. It's my fault because I deliberately made a bad choice here. Rather than fix the previous problem, I'm going to look at a more complicated version. I'll have a quadratic in it, like I did in the bad choice there. I'm going to look at the integral of 3x squared plus 5x plus 1 times e to the x. I'm not going to make the same mistake twice. I'm going to let the u be 3x squared plus 5x plus 1 and dv be the rest of the factors. Derivative of u with respect to x is 6x plus 5. Pretending that these are fractions, du will be 6x plus 5 multiplied by dx. Now, this is interesting because in everything else we've done so far, the du was a constant multiple of the dx. In some cases, it was actually equal to dx. This is not the case here. The du actually has, honest to goodness, x dependence in it. So we're going to have to see what happens about that. On the other hand, dv is e to the x, dv dx is e to the x, v is an integral, v is e to the x. So if I write down my integration by parts formula, this is u times v minus the integral of v du. Two things about that one. Firstly, I don't know how to do that integral. But secondly, it is simpler than the original. The original had a quadratic polynomial multiplying the e to the x, and this one has only a linear one. So it's gotten better, but I don't yet know exactly what I ought to do about this. A clever person would look at that last integral all by itself and say, I'm going to do integration by parts on it to figure out the last integral. So let me write down what we know so far. The integral that we want is this quantity, which is an ordinary function of x, that doesn't cause us any worry, minus the integral of, I'm going to write the factor of 6x plus 5 first, then the e to the x, then the dx. It doesn't make any difference, but it helps me keep things straight. What about that last integral? What about the integral of 6x plus 5 e to the x dx? I'm going to let u equal 6x plus 5. This u has nothing to do with the preceding u. dv will be the rest of the factors, including the dx. Obviously, doing the calculations, du is going to be 6 times dx, and v is going to be e to the x. I like this a lot better because now this looks very much like those easier ones that we were looking at previously. So doing integration by parts just on that last piece, I find out that the antiderivative of that last piece is 6x plus 5 times e to the x minus integral of e to the x multiplied by 6 dx. And I'm happy with that. The new version of the last integral is e to the x times 6 inside. Pull the 6 out, and antiderivative of e to the x is e to the x. So the integral that we needed to calculate to complete our work on the original one is 6x plus 5 times e to the x minus 6 e to the x. Going back and putting this in with our previous work, this is the antiderivative I'm looking for. Of course, the first two pieces have a factor of e to the x. There are terms that can be combined. When the dust finally settles after you do the algebra, you find out that your antiderivative is 3x squared minus x plus 2 times e to the x plus the constant of integration. By now, you know what you should do. Take the derivative of your answer and make sure it's what it's supposed to be. You'll have to use the product rule as usual, but when the dust settles, you find out that the derivative of your answer is 3x squared plus 5x plus 1 multiplied by e to the x, and that's the function you were integrating to start with. So it worked. This has been part one of the integration by parts part. Coming soon, part two. Depending on how it goes, I may have just part two, or there may even be a part three. But by the end of the parts that we look at, we'll be very familiar with integration by parts. I hope everyone has a good weekend. I'll talk to you again soon.